In section 6.5, we're going to look at what we call the central limit theorem. The central limit theorem says that suppose the random variable x has a distribution which may or may not be normal, and suppose it has a mean mu and a standard deviation sigma. Simple random samples of all the same size n are selected. Then the distribution of sample means of those samples will, as that sample size increases, approach a normal distribution. Also, the mean of all sample means is the population mean, and the standard deviation of all sample means is sigma divided by the square root of the sample size n. Some practical rules to follow. If the original population is not normally distributed, for example, our dice rolling example that we used in the previous section, then for n greater than 30, the distribution of sample means will be approximately normal. As n gets bigger, the distribution of sample means gets even closer to being a normal distribution. If the original population is normal, then for any sample size, the distribution of sample means will be normal. So a couple things about notation. We've got two notations for the mean now, but they mean different things. So if you look at this one on the left here, the mu with a sub x bar, this is the mean of the sample means. So x bar is our sample means, and we want to talk about the mean of all those means. But it turns out, if we could get to the population mean of all those means, if we could do infinitely many samples, that the mean of sample means would equal the mean of the population that we originally had. Also, it's the standard deviation of the sample means is the standard deviation of the original population, but divided by the square root of our sample size n. Let's take a look at this example. If IQ scores are normally distributed with a mean of 100 and a standard deviation of 15, let's find the probability of randomly selecting a person with an IQ score of at least 133. That is to say, we're going to try to find the probability of choosing a person with an IQ score greater than 133. So we first want to convert our IQ score 133 into a z-score that we can look up on the table. So that is 133 minus 100 divided by 15 gets us 2.2. Now keep in mind, if I look up 2.2 on the normal distribution table, that's going to get me the probability of being less than 2.2, or on this, in this example, the probability of an IQ score being less than 133. So it's not exactly what I want yet, but all I have to do to find the probability that my IQ score is greater than 133 is subtract 1 minus 0.9861. So that gets me 0.0139. That's the probability that I would randomly select a person with an IQ score greater than 133, or at least 133. Now suppose we selected 9 people and we wanted to find the probability that their mean IQ score is less than at least 133. Now if you think about it, selecting 9 people with a mean IQ score of at least 133 is probably going to be less likely than picking one person with an IQ score of at least 133. But let's take a look at the math of this. Now I want to compute the z-score, however I'm looking at a sample of people. So instead of using the standard deviation of one person, I need to find the sample standard deviation, which we said earlier was my standard deviation of my population divided by the square root of the sample size. So that is, I'm going to have a similar calculation, 133 minus 100, divided by 15 over the square root of 9, because my sample size is 9. And just as a side note, we're looking at the mean of sample means here. However, we said that's the same as the population mean, so we're using 100 still for our mean. Okay, continuing this calculation, we get 33 over 5, which comes out to 6.6. Now if we look up 6.6 on our table, again, this will get us the probability of choosing randomly selecting 9 people, and their mean IQ score is less than 133. So looking this up on our table, we get 0.9999. In other words, it's very likely that if we randomly select 9 people, their mean IQ score is going to be less than 133. So to answer this question, we want to find the probability that the mean IQ score is greater than 133. We just subtract 1 minus 0.9999. As an introduction to hypothesis testing, let's first revisit this idea of the rare event rule. We've seen this a couple times. If we assume a population has a certain mean, and a sample mean is found to have a very small probability, then we conclude that the original assumption is incorrect. Let's look at an example. Suppose Coke says that they filled their cans with 12 ounces of Coke. We're going to take this to be the population mean. And suppose you take a random sample of 36 cans and find your sample has a mean of 12.19 ounces. Suppose we knew that the population standard deviation is 0.11. How likely is it that you would find a sample of 36 cans with a mean of 12.19 ounces or greater? So we're going to use our sample z-score calculation that we found. That is, we're going to divide the standard deviation by the square root of our sample size, which in this case is 36. But otherwise, we're going to plug in 12.19 for our mean, for our x, that we're trying to find the z-score for. Our mean is going to be 12. That's what we're saying that Coke is telling us they fill their cans with. So that's what we're assuming the mean is, and 12.19 is what we found the mean to be in our sample. 0.11, of course, is our standard deviation, but we need to divide that, in this case, by the square root of our sample size, because we did take a sample here. So, running through the calculations and plugging this into my calculator, I get the z-score is 10.36. Now, if I go to look this up on my table, of course, 10.36 is far too big a z-score to be on the table. So we can just say that the probability of a z-score being less than 10.36 is 0.9999, which means that in this case, the probability that my sample mean would have been less than 12.19 should have been 0.9999. Which in turn means that if I'm answering the question, the probability that my mean was greater than 12.19, 1 minus 0.9999 is 0.0001. In other words, it was very unlikely that I got a sample mean greater than 12.19 or greater than. What this means is that most likely Coke is actually filling their cans with slightly more than 12 ounces. And this could be for a number of reasons. Probably, most likely, to avoid any lawsuits of anybody coming and claiming that they filled their cans with less than 12 ounces. So they put a slight bit more in just to avoid any issues with lawsuits. But this is a good introduction to this idea of hypothesis testing. So if the hypothesis was that the mean number of ounces was 12, and we could test that to see if that's actually the number of ounces they're putting in their cans by just picking 36 cans and finding the probability that we would get the mean that we did given those 36 cans and the mean that Coke tells us.